Welcome to DAR Tutors for online and home tuition. Today we're covering a fundamental topic in IB Mathematics AIHL, estimation and confidence intervals. The learning objectives for this video are twofold. First, you will be able to construct and interpret confidence intervals for a population mean, EM, when the population standard deviation, S, is known. Second, you will learn to use these confidence intervals to test claims about a population mean. These skills are essential for making informed conclusions from sample data. Let's begin by understanding why we need confidence intervals in the first place. Often, we are interested in a specific characteristic of a large group or population, such as its mean. For example, a milk company might claim the mean protein content of its 1-liter cartons is 39 grams. The true population mean, M, is a single fixed value. However, we can't possibly test every carton of milk. So we draw a random sample, say 60 cartons, and measure their protein content. This gives us a sample mean, which we call X bar. Suppose our sample mean is 38 grams. This sample mean is a point estimate for the population mean. It's our best guess for milk. But is the true population mean actually 39 grams? Our sample mean of 38 grams is close, but it's not exactly 39. Is this difference due to chance, or is the company's claim incorrect? A single point estimate like 38 grams doesn't tell us how close it's likely to be to the true mean. A confidence interval solves this by providing a range of plausible values for the population mean. So, a confidence interval is an interval of values between two limits, with a percentage that indicates our confidence that the true population mean lies within that interval. For example, we might construct a 95% confidence interval and find it to be from 37 grams to 40 grams. This means we are 95% confident that the true population mean protein content lies somewhere between 37 and 40 grams. How do we construct these intervals? The foundation for confidence intervals is the central limit theorem. The central limit theorem, or CLT, states that for a sufficiently large sample size n, the distribution of all possible sample means, X bar, is approximately normal. Its mean is the population mean M, and its standard deviation is the population standard deviation C, divided by the square root of the sample size n. This standard deviation is a critical measure called the standard error of the mean. It quantifies how much a sample mean is likely to differ from the population mean due to random sampling. So, the CLT tells us that the sample mean X bar follows a normal distribution with a mean of ATE and a standard deviation of S divided by root n. We write this as X bar is approximately normal with mean M and variance Sn squared. This allows us to convert any sample mean to a z-score using the formula. Z equals X bar minus M divided by the standard error set E divided by root n. This z-score then follows the standard normal distribution n0, 1. This transformation is the key to calculating confidence intervals. Now, let's derive the formula for a general confidence interval for the mean M. We want to find an interval that contains me with a certain probability, called the confidence level. We'll denote this confidence level as 1 minus alpha. So, our goal is to find an interval such that the probability of the true mean being within that interval is 1 minus alpha. From the central limit theorem, we know that the z-score is standard normal. Therefore, we can find a critical value, which we'll call z sub alpha over 2. This value, z alpha over 2, is the positive z-score such that the area under the standard normal curve between negative z alpha over 2 and positive z alpha over 2 is equal to our confidence level, 1 minus alpha. This means the probability of a standard normal variable z being between these two critical values is 1 minus alpha. Next, we substitute our z-score formula into this probability statement. We replace z with X bar M OS. Now our task is to rearrange this inequality to solve for m. First, we multiply all parts of the inequality by the standard error, c divided by root n. Next, we subtract the sample mean, x bar, from all parts. Finally, we multiply by -1, which reverses the inequality signs. This gives us the probability statement for the confidence interval for m. To get the actual interval, we replace the random variable x bar with our observed sample mean, which we also call x bar. This results in the general formula for a confidence interval for the mean. The sample mean x bar plus or minus z alpha over 2 times the standard error. The value z alpha over 2 times ses divided by root n is known as the margin of error. This formula allows us to calculate an interval estimate for the population mean with a specified level of confidence. Let's look at the most common confidence level, the 95% interval. For a 95% confidence level, our confidence level, 1 minus alpha, is 0.95. This means alpha is 0.05, and alpha over 2 is 0.025. We need to find the critical value, z sub 0.025, which corresponds to the z-score that leaves an area of 0.025 in the upper tail of the standard normal distribution. Using a calculator or standard normal tables, we find that the z-score for an area of 0.025 in the upper tail is approximately 1.96. Due to symmetry, the critical values are positive and negative, some 1.96. Plugging this value into our general formula, the 95% confidence interval for m is the sample mean x bar, plus or minus 1.96 times the standard error. So the lower limit is x bar minus 1.96 times as over root n, and the upper limit is x bar plus 1.96 times as over root n. Let's work through an example. Suppose a sample of 60 yabbies was taken from a dam. The sample mean weight was 84.6 grams. The population standard deviation is known to be 16.8 grams. We need to construct a 95% confidence interval for the population mean weight. First, we identify our known values. The sample mean x bar is 84.6, the population standard deviation sigma is 16.8, and the sample size n is 60. The confidence level is 95%. We substitute these values into our 95% confidence interval formula. Calculating the margin of error, 196 times 16.8 divided by the square root of 60 gives approximately 4.239. The lower limit is 84.6 minus 4.239, which is about 80.361. The upper limit is 846 plus 4.39, which is about 88.839. So we are 5% confident that the true population mean weight of yabbies lies between 80.4 grams and 88.8 grams. It's crucial to understand what a confidence level, like 95%, truly means. Let's imagine that we repeat our sampling process many times. Each time, we take a new random sample of size n and calculate a new confidence interval. The 95% confidence level means that over these many repetitions, approximately 95% of the confidence intervals we construct will contain the true population mean. However, this also implies that about 5% of our intervals will not. This diagram illustrates this concept. We have a true population mean m. We take multiple samples, calculate a confidence interval for each. The intervals for sample means x bar 1, x bar 2, and x bar 3 all successfully capture m. But the interval for x bar 4 misses me entirely. This is that % chance. So when we report a single 95% confidence interval, like the Yabbie example, we cannot say there is a 95% probability that this specific interval contains the true mean. That's because the true mean is fixed. It's either in the interval or it's not. The probability is in the method itself. We are 95% confident because the method we used generates correct intervals 95% of the time. The observed sample mean x bar is always at the exact center of the confidence interval. And the margin of error, which we found to be z alpha over 2 times sigma over root n, is the distance from the center x bar to either of the limits. The total width of the interval is twice the margin of error. So far, we've focused on the 95% confidence level, but we can choose any level of confidence, like 90%, 98%, or 99%. The process is the same. We decide on a confidence level, 1 minus alpha. Then we find the critical z-score, z sub alpha over 2, that corresponds to that level. Remember, this value is found using the standard normal distribution and corresponds to the area of the upper tail. Here's a table of common confidence levels and their corresponding critical values. Notice a pattern. As the confidence level increases, the critical value z alpha over 2 also increases. Let's see what effect this has on our interval. Let's take our YABI example again. We have x bar equals 84.6, sigma equals 16.8, and n equals 60. We've already calculated the 95% interval. Now let's construct a 99% confidence interval. This corresponds to a z alpha over 2 value of 2.576. The 99% confidence interval is 84.6 plus or minus 2.576 times the standard error. Calculating this gives us the interval from 78.9 grams to 90.3 grams. Compare the 95% interval 80.4, 88.8 with the 99% interval 79.0, 90.2. The 99% interval is wider. This demonstrates a crucial principle. To be more confident that our interval contains the true mean, we must construct a wider interval. There's a trade-off between confidence and precision. So which confidence level should we use? A wider interval, like 99%, gives us more confidence, but it's less precise. A narrower interval, like 90%, is more precise, but we have less confidence in it. A statistician must choose a level based on the context. If the cost of being wrong is very high, for example in a medical study, a higher confidence level like 99% might be appropriate. If the stakes are lower, a more precise 90% or 95% interval might be preferred. The 95% confidence level is the most commonly used, as it provides a good balance between confidence and precision in many applications. Our discussion has focused on varying the confidence level. The other key variable in our formula is the sample size, n. We know the margin of error is inversely proportional to the square root of n. This means increasing the sample size will decrease the margin of error and thus narrow the confidence interval. A narrower interval is more useful because it gives us a more precise estimate of the population mean. This gives us a powerful tool. We can calculate the sample size needed to achieve a desired level of precision. Let Yu represent the desired width of our confidence interval. We know the width is twice the margin of error. We can rearrange this formula to solve for n. First, divide by 2, then multiply by root n and divide by w. Finally, square both sides. This gives us a formula for the required sample size. N equals the square of the quantity, 2 times z alpha over 2 times sigma, divided by the desired width of u. Let's apply this to our YABI example. What sample size is required to find a 95% confidence interval for the mean YABI weight m, with a width of only 5 grams? Remember, sigma is 16.8, and for 95% confidence, z alpha over 2 is 1.960. Plugging these values into the formula, we get n equals the square of 2 times 1.960 times 16.8 divided by 5. This calculation results in approximately 173.5. Since we can't sample half a YABI, we must always round up to the next whole number. Therefore, a sample size of 174 is required to achieve a 95 for confidence interval with a width of 5 grams. This shows that increasing the sample size from 60 in our first example to 174 gives us a much narrower, more precise interval. However, larger samples are more expensive and time-consuming. There's a balance to be struck between accuracy and practicality. So far, we've focused on estimating a population mean. Now, let's see how we can use a confidence interval to formally test a claim about a population mean. The method is quite straightforward. We start with a null hypothesis, H0, which states that the true population mean m is equal to some specific value m0. The test works like this. First, we construct a 95% confidence interval for the true mean m, based on our sample data. Second, we look to see if the value m0 from our null hypothesis lies within the interval. If it does not, we reject the null hypothesis at the 5% significance level. If it does lie within the interval, we do not reject the null hypothesis. It's very important to note the conclusion when the value is within the interval. We do not say we accept the null hypothesis, only that we do not reject it. A confidence interval shows us what values are plausible. If m0 is among them, it's a plausible value. But there could be many other plausible values too. This means that if the null hypothesis value m0 is contained in our 95% confidence interval, it suggests that ma0 is a plausible value for the population mean. In statistical terms, the difference between our sample mean x bar and the claimed mean m0 is not statistically significant. Let's work through an example. A machine dispenses milk into cartons. The mean volume m is supposed to be 1005 ml, and the standard deviation s is 10 ml. A quality controller samples 25 cartons and finds their mean volume to be 1002 ml. Does this sample provide enough evidence to suggest the machine is no longer dispensing 1005 ml? Our null hypothesis is that the true mean volume m is 1005 ml. Our sample data gives us a sample mean of 1002 mE, a standard deviation of 10 mE, and a sample size of 25. We'll use a 95% confidence interval to test the claim. First, we construct the 95% confidence interval for me. This is 1002 plus or minus 1.96 times 10 over the square root of 25, which is 5. This calculates to an interval from 998.08 to 1005.92. Now for the second step. Check if m0 equals 1005 lies within this interval. The interval is from 998.08 to 1005.92. The value 1005 is clearly inside this interval. Since m0 is within the 95% confidence interval, we do not reject the null hypothesis. We do not have sufficient evidence at the 5% level to conclude that the machine's mean dispensing volume is no longer 1005 ml. Despite the sample mean being lower, the difference is not statistically significant. It could have happened by chance. Let's summarize what we've learned. We've learned to construct confidence intervals using the formula x bar plus or minus z alpha over 2 times the standard error. We've seen that confidence level determines the critical z-score, and sample size determines the standard error. Increasing confidence or precision by decreasing interval width are competing goals. We've also learned to use confidence intervals to test claims. Reject the null hypothesis if the claim population mean is not in the confidence interval. We've met our learning objectives. You can now build and interpret confidence intervals and use them to test hypotheses. It's time to put your knowledge to the test. Let's look at some IB-style practice questions. Question 1. A random variable x has a population standard deviation of 7. To test the claim that the population mean m is 50, a random sample of 60 is taken, and the sample mean is 49.1. Part A, construct a 95% confidence interval for me. Part B, use the confidence interval to assess the claim that m equals 50. Here's the solution to question 1. First, we list our knowns. Sigma is 7, the sample mean x bar is 49.1, and the sample size n is 60. For a 95% confidence level, the critical value z alpha over 2 is 1.960. We apply the confidence interval formula. The lower limit is 49.1 minus 1.960 times the standard error 7 over root 60. The upper limit is 49.1 plus the same amount. This gives us the interval from 47.33 to 50.87. For part B, we assess the claim. The claimed value for the mean is mu0 equals 50. We check if 50 is inside our interval 7.335087. It is. Since the claimed value 50 is within the 95% confidence interval, we do not reject the null hypothesis. There is not sufficient evidence at the 5% significance level to dispute the claim that the population mean is 50. Question 2. Bags of salted cashew nuts are advertised to have a net weight of 100 grams. The manufacturer knows the standard deviation of weights is 1.6 grams. A quality control manager samples 40 bags and finds their mean net weight is 99.4 grams. Part A, construct a 95% confidence interval for the mean net weight. Part B, use the confidence interval to test the claim that the mean net weight is 100 grams. Here is the solution to question 2. For part A, our knowns are sigma equals 1.6, x bar equals 99.4, n equals 40. For a 95% confidence level, Z alpha over 2 is 1.960. We calculate the confidence interval. The margin of error is 1.960 times 1.6 over root 40, which is approximately 0.495. The interval is 99.4 plus or minus 0.495, giving us 98.905, 99.895. For part B, the claim is that the true mean is 100 grams. We look at our interval 98.905, 99.895. The value 100 is not contained in this interval. It is outside to the right. Because the claim mu equals 100 is outside the 95% confidence interval, we reject the claim at the 5% significance level. The difference between the claimed mean of 100 and the sample mean of 99.4 is statistically significant. The manager has evidence to conclude the bags are, on average, lighter than advertised. Question 3. Sophie took a sample of measurements. Her 95% confidence interval for the population mean was from 27.6 to 31.8. Part A, find the sample mean x bar. Part B, if the population standard deviation was sigma equals 6, and she had used a 99% confidence level, find the sample size she must have used, and the confidence interval she would have calculated. Here is the solution to question 3. For part A, we use the fact that the sample mean x bar is always the midpoint of the confidence interval. We find it by adding the lower and upper limits and dividing by 2. This gives us x bar equals 29.7. For part B, we are given sigma equals 6. We know the 95% confidence interval is x bar plus or minus 1.960 times sigma over root n. From part A, we know x bar is 29.7. We can calculate the margin of error from the given interval as the upper limit minus the sample mean, which is 2.1. Now we have an equation. 2.1 equals 1.960 times 6 over root n. Solving for root n, we get root n equals 5.6. Squaring both sides, n is approximately 31.36. We must round up, so the sample size was 32. Finally, we calculate the 99% confidence interval using this sample size. The critical value for 99% confidence is 2.576. The interval is 29.7 plus or minus 2.576 times 6 over root 32. This gives us the wider interval of 26.8, 32.6. Question 4. The time it takes Joan to run 100 meters is normally distributed with a mean of 12.46 seconds and a standard deviation of 0.3 seconds. She trains for 6 weeks, and her mean time from 12 trials is now 12 and 18 seconds. Part A. Assuming the standard deviation has not changed, construct a 95% confidence interval for Joan's new mean time. Part B. Hence assess the claim that Joan's time has improved, and the claim that Joan is now faster than Betty, whose time is 12.26 seconds. Here is the solution to question 4. For part A, our knowns are the sample mean x bar equals 12.18, standard deviation sigma equals 0.3, and sample size n equals 12. For a 95% confidence level, Z alpha over 2 is 1.960. The confidence interval calculation gives us 12.18 plus or minus 0.166. This results in the interval 12.014 to 12.346. Now, for part B. The first claim is that Joan's time has improved. Improved means her time should be less than her old mean of 12.46 seconds. We check if our entire confidence interval from 12.014 to 12.346 is below 12.46. It is. The highest value in our interval is 12.346. Since the entire interval is below 12.46, we can be 95% confident that her new mean time is lower than her old mean time. Her time has likely improved. The second claim is that Joan is now faster than Betty, who runs the 100 meters in 12.26 seconds. To be faster, Joan's time must be less than Betty's time. We check if our entire interval is below 12.26. The interval is 12.014 to 12.346. The value 12.26 is inside the interval. This means that, based on our sample, it is plausible that Joan's time is faster than Betty's. But it is also plausible that Joan's time is slower, or about the same. We do not have conclusive evidence to state with 95% confidence that she is faster than Betty. Question 5. A manufacturer of bottled water dispenses water into 1-liter bottles with a standard deviation of 2.3 millimils. A sample of 30 bottles produces a mean of 1,001 mils. Part A. Construct a 95 for confidence interval for the population mean contents. Part B. Find the width of the interval. Part C. It is decided that the 95% confidence interval must have a width of less than 0.5 mg/I. What sample size is required? 2. What problems may result from obtaining a narrower CI? Here is the solution to question 5. For part A, we have sigma equals 2.3, x bar equals 1001, and n equals 30. For 95% confidence, z alpha over 2 is 1.960. The confidence interval is 1001 plus or minus 1.960 times 2.3 over root 30. This gives us the interval 1001t 1001a2. For part B, the width of the confidence interval is twice the margin of error. From part A, we calculated the margin of error to be 0.82 millios. Therefore, the width is 2 times 0.82, which is 1.64 milal. For part CI, we need to find the sample size required for a 95% confidence interval with a width less than or equal to 0.5 milal. We use the sample size formula n equals the square of 2 times 1.960 times 2.3 divided by 0.5. This calculates to approximately 324.4. Rounding up, a sample size of 325 bottles is required. For part CTE, what problems might result from obtaining a narrower confidence interval? A narrower interval is more precise, which is good, but it comes at a cost. It requires a much larger sample size. Taking a sample of 325 bottles instead of 30 would be more time-consuming, more expensive, and could be impractical in a real-world manufacturing setting. Question 6. Sophie took a sample of measurements of a random variable x. Her 95% confidence interval for the population mean was from 27.6 to 31.8. The population standard deviation was sigma equals 6. Part A, find the margin of error, E, and the sample size, N. Part B, suppose she takes a new sample of 50. Her new sample mean is 30.5. Construct a 98% confidence interval for the population mean with this new data. Here is the solution to question 6. For part A, we know the sample mean x bar is 29.7 from question 3. The margin of error, E, is the upper limit minus the sample mean, which is 2.1. We use the formula E equals 1.960 times sigma over root n to find n. Solving for n, we get n equals 32. This also matches our result from question 3. For part B, Sophie has a new sample. The new sample mean x bar is 30.5. The sample size n is 50. The population standard deviation sigma is still 6. We want a 98% confidence interval. From our table of critical values, z alpha over 2 for 98% is 2.326. We calculate the new confidence interval, 30.5 plus or minus 2.326 times 6 over root 50. This gives us the interval 28.53, 32.47. Notice that this interval is wider than the 95% interval with a sample size of 32 from our earlier example due to the higher confidence level. It is now approximately 10 minutes into the video. Before we conclude, we would like to invite you to contact DAR Tutors for expert, personalized tuition. Our experienced tutors provide tailored support for the IB, A-Level, and IGCSE curricula. Whether you need to clarify a concept, prepare for an exam, or improve your problem-solving skills, DAR Tutors can help you achieve your academic goals. For expert tuition in these subjects, please visit our website or send us an email. Thank you for watching.